Local maxima and minima. So local maxima and minima of a function are going to be important places that give us valuable information about a function and how it behaves. A function is said to have a local maximum at p, point p, so that's an independent value here, if f of p is greater than or equal to the values of f of x near p. So that means that it's going to be the highest point in a small area. So try to envision what that might look like. A function is said to have a local minimum at p if f of p is less than or equal to the values of f of x near p. So again, try to envision what that might look like. You have a point that's the lowest point in a small area. Now, near p is the condition of these two definitions that make these local maximums and minimums. When you think of the word maximum, I'm guessing you think of the absolute biggest of something. And when you hear the word minimum, you think of the smallest of something. Well, that's still true here, only now that something is in a small area. So we're looking for the biggest value of a function in a small area and the smallest of a function in a small area. So when we do this, there's a couple things you need to remember about local maximums and minimums. First, functions can have more than one of these. You can have multiple local maximums or local minimums. Secondly, local maximums and minimums don't need to be the absolute highest and lowest values of the function. That has another name. That's going to be called global maximums and minimums, and we'll talk about those later in the term. So let's take a look at a picture and see if we can visualize what these local maximums and minimums look like, so then we can start discussing how we're going to find them and what sorts of things we can do with them. Consider the graph of f of x seen here. When we talk about a local maximum, we're talking about a point like this one right here that happens a little bit before 0.5, so maybe 0.4. You can see that it looks like it has a hill shape. It's the highest point in that small area. Similarly, if you look pretty close to -1, so maybe -0.9, and again at 1.3-ish, these are local minimums. And these local minimums, you can see, have this cup shape. So they're the lowest y value in a small area. But that doesn't mean that they have to be the lowest y value on the entire function, because you can see that the one at 1.3-ish is certainly not as low as the one at -0.9. So when we talk about local, we're really looking for these hills and these cups, because that's what's going to visually cue us in that we have a local maximum or minimum. Now, there's something really interesting about these points. I want you to think about what the first derivative at each of these points is going to be. If I were to draw in the tangent line at each of these points, something really interesting happens. I notice that at all the places where I have my local maximums and minimums, that the tangent lines are all horizontal. So they all have a slope of 0. It turns out that that's not a coincidence. The first derivative is going to be 0 whenever we have a local maximum or minimum. And we're going to be able to use that to help us figure out where these things might be located if we don't have a picture. So it turns out that these places where the first derivative equals 0 has a special name to help us start calculating to find them and to identify where they might be for our use. So let's take a look at that. A critical point, p, for a function f of x is a point in the domain of f of x where f prime of p equals 0 or f prime of p is undefined. So now these places where our first derivative equals 0 are going to be called critical points. So the critical point is the independent value. So it's usually x, but it could be t or p or q depending on the function. But again, that critical point is going to be where the first derivative equals 0 or is undefined. Usually we're going to get these undefined cases when we do something like the quotient rule, because the quotient rule provides us with a function that has a denominator, and we know that if a denominator equals 0, then the function is undefined. However, most of the time when we're solving for critical points, we're going to be looking for where the first derivative equals 0, since the majority of the functions we work with are continuous and don't end up with undefined points. A critical value of f of x is the y value that you get from plugging your p back into the original function. So again, f of p is going to be called the critical value. So if you know where your critical point is in terms of x, you can plug it back into the original function, and that will give you the critical value at that point. So we want to get really good at finding out where critical points are, because once we're comfortable locating where they are, we can then use them to try to determine whether or not we have local maximums and minimums, which is our ultimate goal. So for this part of the video, we're going to be looking at how we can use various means to solve for critical points, which will be the first step in most of the things we do when we're looking for local maximums and minimums. So let's try some examples. Suppose f of x equals 3x squared plus 6x plus 1. Find all the critical points of this function. So again, to find a critical point, we're interested in where the first derivative equals 0 or where the first derivative is undefined. So my first step whenever I'm looking for critical points is to find the first derivative of the function if I don't already have it. So here, when calculating my first derivative, I'm going to use my power rule. So the derivative of 3x squared is 6x, and the derivative of 6x is 6. The derivative of 1 is 0 because 1 is a constant. Looking at this first derivative, there's nothing about it that leads me to believe that there would be any points where this is undefined. In fact, this derivative is defined for all values of x. So that means I can just look for where this first derivative equals 0. So I'm going to take my first derivative and set it equal to 0. Now I'm going to do the algebra to solve for x. I'm going to subtract 6 to the right, and then I'm going to divide both sides by 6, and I get x equals -1. So the function 3x squared plus 6x plus 1 has one critical point, and it happens at x equals -1. Now, if you know anything about x squared, if you can envision what x squared looks like, then you have a pretty good sense that it would have one critical point, because x squared has a U shape, and so here we're expecting one horizontal tangent line. So here I had one critical point, and there's a relationship between the leading power of the original function and the number of critical points that I have. So here, my leading power, which is the biggest power of the original function, is 2. You're always expecting one less than the leading power. So it's most likely that this function will have one critical point. There are some cases where this doesn't work, but in general, it's a good rule of thumb. So let's try another example. Example 2. Suppose f of x equals 2x cubed minus 3x squared minus 36x plus 14. Find all the critical points of this function. So again, I have a polynomial, and I see that the leading power of my polynomial is 3. Since the leading power is 3, I'm expecting 2 critical points, so one less than the leading power. Let's see if that holds true once I do my algebraic work. So again, I'm interested in where the first derivative equals 0 or where the first derivative is undefined. So here, my first derivative, I'm going to again use the power rule. I'm going to get 6x squared minus 6x minus 36. And I want to know, when does that equal 0? So again, I just want to point out that this polynomial function is defined for all values of x, so I don't need to worry if it's undefined anywhere. There's nothing here that leads me to believe that there's any places that it would be undefined. So I set my derivative equal to 0, and now I notice that I have a quadratic. So I have two options at this point. I can use the quadratic formula to find the roots, or I can factor it. Either way, I need to use algebra to find when this is going to equal 0. So I'm going to factor this. So here, I'm first going to factor out the 6 to see if that helps me factor things down a little bit easier. So factoring out a 6 leaves me with x squared minus x minus 6. And I still want to know, when does that equal 0? So factoring that down one more time, I get x minus 3, x plus 2. And still, I want to know When does that equal 0? So now I have three things multiplied together: 6, x minus 3, and x plus 2. In order for that to equal 0, one of those terms has to equal 0. Well, I know that 6 doesn't equal 0 because 6 equals 6. So I can take each factor and set them equal to 0 to get my critical points. So if x minus 3 equals 0, that tells me that x would have to equal 3. If x plus 2 equals 0, that tells me that x would have to equal negative 2. So this function has two critical points, or two places where we're going to have horizontal tangent lines. One at x equals 3, and one at x equals negative 2. You should feel comfortable factoring and finding roots of quadratic equations, as this is something that we are going to continue to do throughout this course. Let's look at another example.